Okay, so now we're going to look at sketching curves in polar coordinates. In the last video we looked at the polar coordinate system and how to plot points in this system. And now we're going to look at how to plot collections of points, which are going to form curves. What would be a collection of points? Well, if we consider an equation, something like r equals f of theta, and we ask for what are all the points that satisfy that equation? What are all the r and theta values that satisfy that equation? That'll construct a curve. And we're interested in trying to plot these things now. So here's some examples of some curves. R equals sine 3 theta. It's got this sort of 3-leaf flowered kind of structure. 2 sine theta. You got this 4-leaf one, 5 sine theta, or sine 5 theta. It's got this 5-leafed one. There's a 1 plus cos theta. It's called a cardioid because it kind of looks like a heart. At least if you turn your head sideways, it'll look like a heart. Different variations on that. All of these ones may not look like it right now, but all of these ones we'll be able to plot by hand. We'll be able to look at this equation and be able to construct the plot by hand. That's really cool. I'll show you how to plot these things using graphing utilities as well. GeoGebra, for example. I'll show you how to do this in GeoGebra. Some of these things, though, I just want to point out some characteristics. Before we go into the full-blown sketching of these things, let's just look at a few characteristics of this. Let's just pick this middle one, r equals sine 2 theta. Let's look at this point out here. What's that distance? How can we figure that out? Well, you got to start to switch the way you think about distances now in polar coordinates. Distance is the r value. What's so special about this point way out here? Well, it looks like it's got the biggest r value. The point pulls away. Out of all these points on this leaf, it's the one that's the r value is the biggest. Out of all the points on this leaf, it looks like this very tip is the one where the r value is the biggest. So I look at my r value. It's given by sine of 2 theta. When is sine of 2 theta the biggest? Well, first of all, sine is biggest when its value is 1. So that immediately tells me that that distance has to be 1. Moreover, when does sine of an angle become 1? Well, first it happens when the angle is pi by 2. So let me just think about this. When the angle, the thing I'm putting into the sine function, is pi by 2, sine of it will be 1. So when is 2 theta equal to pi by 2? Oh, well, that's when theta is pi by 4. Oh, so I know that that's got to be pi by 4 then. Because if I plug pi by 4 into this expression, I get sine of pi by 2, which is 1. So I get that. And so I can start to immediately pick off other things here. That angle would be 3 pi by 4. 3 pi by 4. This angle down here, it would be negative pi by 4. So I can start to pick off all of these properties. Again, for these ones, what's the biggest distance here out to that tip? Well, that would be the maximum value of sine. That again would be 1. How about for this one here? Well, this is kind of cool because we've sort of got 2 different leaves. And we're going to see that we can actually sketch this one by hand. And that's kind of interesting in and of itself. But what would the biggest value be out here? Well, let's think about it. I want this thing to be biggest as possible. I'm taking 1 minus something. Well, if the cosine was negative 1, that's as small as it could possibly get in terms of the negative values, then this would be negative 1 times negative 2, so that's positive 2 plus 1 is 3. So the biggest this thing could get is a value of 3. So that's what that distance has to be here. That has to be a value of 3. What about this short little distance here? How does that happen? Well, I would take 1 minus, well, if cosine was negative 1, then, or sorry, if cosine was 1, then you'd have something like 1 minus 2, which is negative 1. Maybe that point there is coming from something out here, but the r value is negative, so it slingshots me to the other side. Maybe that's what it is. So that's an r value of 1. So we can pick some of these features off just by looking at the corresponding equation, but thinking of now r is distance and theta is this rotational angle. Okay? So I just wanted to give you a bit of a starter on how you should get your sort of mind in place for looking at these things. And now we're going to go ahead and start sketching graphs, working our way up to things like this. So what curve is represented by the polar equation r equals 3? Got our polar coordinate, well, our plane here, and I'm using the Cartesian coordinate grid, or axes, as a frame of reference for my polar coordinate system. What is r equals 3? Well, those are all the points whose r value is 3. All the points whose distance is 3 from the pole. So there's a whole circle of points whose distance is 3 from the pole. That's r equals 3. We're starting to see, with this example, what is interesting about the polar coordinate system. If you think about the Cartesian coordinate system and an equation like y equals 3 or x equals 3, those give you straight lines. Y equals 3 would be a horizontal line. X equals 3 would be a vertical line. Those are essentially the sides of rectangles that we have in that system, hence the name the rectangular coordinate system. In this system, if we take one of the variables and set it constant, like r equals 3, then we get circles. So in some sense, circles are the basic objects in this coordinate system. And that's what this coordinate system is useful for. It's for representing things that are sort of circling or spiraling around the pole. Okay, so for that matter, I mean, why don't we just go with the next one? What is the curve given by this equation? Theta equals 3. Theta equals 3. What is the curve given by that? Actually, I'm going to change it from 3 to maybe an angle that we might be more used to working with. Theta equals pi by 4. What is this? Theta equals pi by 4. Well, we want all the points r theta where the theta value is pi by 4. So these are all the points whose r value is positive. That's pi by 4 there. But we could also have points like -1 pi by 4 or -2 pi by 4. So we could have all of those negative r values appearing as well. And so there is our curve, theta equals pi by 4. So the basic objects in this coordinate system are, when r is constant, it's a circle. When theta is constant, it's a straight line through the origin. So lines through the origin and circles are the basic objects in the Cartesian coordinate system. Just for fun, I mean, this wasn't asked in this question, but you know, one of the most basic objects you do in the Cartesian coordinate system afterwards, after looking at y equals a constant or x equals constant, is to say, well, what about y equals x? What does that look like? Of course, that's a straight line through the origin of slope 1. What about in this system? What is something of the form r equals theta? Well, let's think about that. What would r equals theta look like? So I'm going to imagine theta moving. So when I'm on the polar axis, my theta value is 0. So my r value is 0. So I'm right at the pole. And then as theta starts to increase, as my angle starts to increase, my r value starts to get bigger. So it starts to spiral out like this. And then when I hit this point, my theta value is pi by 2, but so is my r value. And then my theta value starts to increase, but so does my r value. Because as theta increases, so does my r value. And as theta increases, my r value keeps increasing, and so on. And so what's happening is this equation, r equals theta, is a spiral. Something spiraling away from the pole as the theta values increase. That's pretty neat. That's pretty neat. Another basic object. So basic objects are circles, lines, spirals, things that are circling around the origin, but we also get these straight lines through the origin as well, based on theta being constant. So let's now look at a few more examples of curve sketching. So let's sketch the graph of the curve r equals 2 sine theta. Now what we typically do to get going with sketching these curves is to first start with in a place of familiarity, that is in the Cartesian coordinate system. So I'm going to start by sketching it in the Cartesian coordinate system. The only reason I want to sketch it there is because I want to get a feel for how does r change when theta changes. If you want to think of it in comparison to just the last example, here I was just noticing that as I let my theta value increase, my r value increased. So I was using the fact that there was this relationship between r and theta. And I didn't really have to sketch the graph of this because I could immediately see as theta increases, r increases. But that's the kind of thing I want to have in mind when I'm sketching something like this. I want to know, as theta increases, how does r increase? Maybe I'm going to get a visual of this first. I'm going to get a visual for how theta and r are related. So that means I'm going to sketch it in Cartesian coordinates, in the Cartesian coordinate system. Okay, so we're going to have to be able to sketch these trig functions in Cartesian coordinates. The way I would do this is I say, well, it's the sine function whose amplitude is now 2. So it's the sine function. And its amplitude is now 2, so we're going up 2 units. We're down to -2. What are the main features here? Well, it peaks out at pi by 2. It crosses at pi. It bottoms out at 3 pi by 2, crosses again at 2 pi, and then it just repeats itself. And it keeps going all the way along. So maybe I'll do a few more. So this is 5 pi by 2, 3 pi, 7 pi by 2, and 4 pi. Now that gives me information about how theta and r are related. As theta increases from 0 to pi by 2, I see my r value increasing. So now I'm set to plot this in the polar coordinate system. So let's look at the polar coordinate system. When theta is 0, r is 0. So I'm right here. When theta is 0, r is 0. Now as theta increases, my r value increases, so that when theta hits pi by 2, my r value is 2. So I'm going to end up here having an r value of 2. But in order to get from there to there, I have to sweep out different angles. So as my angles increase to pi by 2, my r value increases. So it looks something like this. My r value, I'm getting farther and farther away from the pole, so that, for example, when I'm out here at theta equals pi by 4, my r value in that case, what is r when theta is pi by 4? That's sine of pi by 4, or in other words, 2 times 1 over root 2, or root 2. So there's my r value. It's root 2. Root 2 is my r value. What if I'm at pi by 6? What's r of 2 sine pi by 6? Well, sine of pi by 6 is root 3 over 2, so this would be 2 times root 3 over 2, or root 3. So I'm even further away. Root 3 is bigger than root 2, so I'm even further away. So I'm up here somewhere. There's my theta is pi by 6, and now my distance is root 3. It's not necessary to throw this extra information there, but I'm just trying to give you an indication of what I'm using, what I'm actually thinking of. As my theta value increases, so does my r value. My r value increases all the way up to 2. So I'm going to indicate this by putting a little 1 here. That little segment that we just looked at corresponded to this piece that I've now sketched. Now let's move on to the next piece, part 2. As theta goes from pi by 2 down to pi, or pi by 2 to pi, the r value drops now to 0. So my r value is now dropping down to 0, so that when I finally hit pi, a theta value of pi, I'm right at the pole again, because my r value is 0. I'm distance 0 from the pole. And so that's segment 2. So far, so good. Now what about segment 3? Segment 3, as my theta value goes from pi to 3 pi by 2, as I trace out angles in this quadrant 3, my r value goes from 0 to -1. So here's where things get interesting. My r value is negative. If my r value were positive, then it would probably look something like this. You know, it would just trace out what it looks like above. But my r value is not positive. My r value is negative. So I had to slingshot to the other side of the pole. So this is not what I have here. Those would be for R values being positive. Instead, I slingshot to the other side of the pole. So I start to trace out what looks like the same portion of the curve again. So this is part 3. Part 3 gives me that portion here. Okay, so at this point it might be worthwhile to sort of see this dynamically. Okay, so here we've got the curve sketched in the Cartesian coordinate system on the left. Watch what happens as that point, as the theta value increases. So we have this point, this green point on the Cartesian curve. Its R value is increasing. If you look on the right, you'll see how we're sketching it in the polar coordinate system. The R value is increasing, so this green point is going to start to pull away from the pole. So as we go up, R values are increasing. We get to a maximum R value of 2. And then from the Cartesian graph on the left, we see that the R value starts to decrease until we hit a theta value of pi where the R value is 0. And so that looks like a perfect circle. And now what happens? Now the R value becomes negative. And I've indicated this here with a dotted line. So this is the positive R values for that corresponding angle theta. The dotted line indicates the negative R values. So I've just called it negative ray here. So let's indicate that those are the negative values. And again, we trace out the circle again, this time with our negative R values, until we hit 2 pi and we're back to where we started. And then it could just keep going and going and going. Here I only let my slider go up to 2 pi, but we could increase it and just see that it keeps tracing it out over and over again. So we saw that because of the fact that we get some negative R values, this causes the circle to be traced out twice. In other words, we don't get this circle down below, which we may have expected to get as we trace through angles from pi to 3 pi by 2, for example. So what if we just play around with this a little bit and say, okay, I had some negative R values here. Let's make them positive. How are we going to make them positive? We can just take the absolute value of this function instead. And notice what happened. For all of these values, so R, as theta goes from 0 to pi, the R values are all positive. We land back at pi, so that means we've traced around the circle once. Well, let's actually just see it. We trace around the circle once. And now we get to pi. And now we're going through angles from pi to 3 pi by 2, and we're still on the positive part of that ray. Positive R values for those corresponding angles. And so we trace out bottom circle. So that's pretty neat. In some sense, without the absolute values, the bottom circle ended up getting folded on top of the top circle. What kind of shape does this look like? To me, it kind of looks like a circle. So here's my question. Is this a circle? Is this a circle? Can we actually show that this is a circle? Well, let's check. Let's check to see if it's a circle. How do we check that? Well, R is 2 sine theta. But what's sine theta? Sine theta is y by r. Oh, so r squared is 2 times y. Oh, but 2 times y, which is r squared, is equal to x squared plus y squared. Ah, there we go. That's a circle. So switching from polar coordinate description into the Cartesian coordinate description, we see that it's actually a circle. What circle is it? It's x squared plus y squared minus 2y. We can complete the square. So x squared plus y minus 1 all squared. If I square this, that's y squared minus 2y plus 1. And so to get rid of that 1, because I introduced a 1 here, if I square this out, I get what I had above plus an extra 1. So I have to take away that 1. So I could take away a 1 and then get it equal to 0. Or I can just Move the 1 to the other side, and there's our circle. It's a circle of radius 1, shifted up 1 unit. So there's a center of 1, and yeah, it's a radius 1, because if that's the center, then we see that the places where it hits above are set 2, so 1 unit above the center, 1 unit below the center. So it is a circle. Okay, so let's look at another example. Sketch the graph of the curve 2 cosine 3 theta. So we'll proceed much like we did in the previous case. I'd like to know how r changes with respect to theta. So we'll go to the Cartesian coordinate system first. So this is cos 3 theta. So I'm going to start with sketching the cosine function. Looks something like this, and so on. And now I'll put in all this scaling information. So its amplitude is 2, so it goes up to 2, down to -2. What's its period? Well, regular cosine function is period 2 pi, but this one's been compressed by a factor of 3. So its period is now 2 pi by 3. So that means one cycle goes out to an angle of 2 pi by 3. And so if there's 4 interesting bits on that one cycle, then 2 pi by 3 divided by 4, which is pi by 6, is that angle, or that first place that something interesting happens. Pi by 6 is where it crosses. Then another pi by 6 later, which is now pi by 3, is where it bottoms out. Another pi by 6 later, which is 3 pi by 6, or pi by 2, is where it crosses again. And then another pi by 6 later, which is 4 pi by 6, or in other words 2 pi by 3, is where it caps out. And then we keep going, adding pi by 6 each time. So this was 4 pi by 6, and that's now 5 pi by 6, 6 pi by 6, 7 pi by 6, 8 pi by 6 is 4 pi by 3, 9 pi by 6 is 3 pi by 2, 10 pi by 6 is 5 pi by 3, 11 pi by 6, 12 pi by 6 is 2 pi. And we can keep going, but I'll stop there. And then you can do the same thing in the other direction. Let's see if we've got now enough information to get our our polar coordinates sketched. So here it is now in polar coordinates. We've got all of these angles here that are places where it seems something interesting is happening. Pi by 6, pi by 3. So what I'm going to do is I'm going to sketch those in. So there's a pi by 6 angle. There's pi by 3. There's our pi by 2. So after pi by 2 was 2 pi by 3, then 5 pi by 6, then pi, then 7 pi by 6, 8 pi by 6, which is 4 pi by 3, then 3 pi by 2, and then 5 pi by 3, 11 pi by 6, and what is 0, but also 2 pi in terms of angles. So there's all our angles that seem to be where interesting things happening, like r value 0 or r values being maximum, positive or negative. Now let's try to see if we can sketch this. And all we're doing at this stage is we're just trying to pull information from the graph above about how does the r value change. Is it growing or is it shrinking as my theta values change? So when theta is 0, the r value is 2. So when theta is 0, I'm out here at an r value of 2 units along. Then what happens? As I move to pi by 6, my r value shrinks to 0. So as I move through angles out to pi by 6, my r value shrinks to 0. Then my r value becomes negative out to a maximum centered at pi by 3. So I'm going to be out to a value of negative 2 on pi by 3, but negative 2 means I'm on the opposite side of the pole. So I'm going to be down here. So I have to spiral out to here. And then I spiral back in so that when I hit an angle of pi by 2, I'm at 0 again. So pi by 2, vertical line here, I've got to come back to 0. So I spiral into 0. So I'm going to start indicating what these were. This was segment number 1, corresponding to that one. Then segment 2, I used to get that piece. And then segment 3, I used to get that piece. And then now we're on segment 4. R value is going from 0 out to 2. Oh, let me really emphasize this here. R is that, theta is this. So as my R value goes from 0, or sorry, as my theta value goes from pi by 2 to 2 pi by 3, my R value goes out to 2. So at 2 pi by 3, I'm going to have an R value of 2. So I'm going to go out here to an R value of 2 as I move through the angle from pi by 2 to 2 pi by 3. So it comes out and hits there. Maybe I'll move it along a bit. It's sort of got to match this distance, so it's probably out here somewhere. There we go. R value of 2. And then as I move, so that was 4, and then for segment 5, my R value goes back to 0 at 5 pi by 6. So it now goes back to 0, 5 pi by 6. And that was segment number 5. What about segment number 6? Now we're moving out as we go through 5 pi by 6 to pi. Our R values are negative, so we're on the opposite side of the pole. When we hit an angle of pi, our R value is going to be negative 2. So it's not out here at 2, it's on the other side of the pole at negative 2. So as I move through the angles from 5 pi by 6 to pi, my R value is on the opposite, my point is on the opposite side of the pole, and my R value goes out to here. So that's 6. And what happens next? Then we go 7. R value goes from negative 2 back to 0. But I'm already out here. As I move through these angles from pi to 7 pi by 6, my R value is negative, so it looks like I trace out that same portion again. So it looks like this is 7. And then 8. And then 9. And then 10. It looks like I'm tracing everything out again. 11 and 12. So 7, 8, 9, 10, 11, and 12. So check that for yourself. Keep moving along and see that you trace it out again. Now all of these distances should be the same from the pole, so this one probably doesn't look so good. It should go nice and far down here, maybe out to, it's got to go out to 2, a length of 2, so just to make it sort of match up. And there we go. We get this, what looks to be a 3-leafed flower. And so there's the sketch of our graph of 2 cos 3 theta. So let's look at this example dynamically again. Here on the left I've got the sketch of the graph in the Cartesian coordinate system, and let's watch what happens as the theta value increases. As we go from theta equals 0 to pi by 6, we're starting to trace out the first leaf. Now the R values are negative, so we're on the negative part of the ray for that corresponding theta value. It's tracing out that third leaf there. Well, I guess the third leaf if we count the leaves in the counterclockwise direction. Now it's starting to trace out the second leaf. And we're coming back to pi now. We're on, you can tell we're at angle pi because we're on the negative portion of the ray. So the ray is approaching, this is the angle theta, this ray represents the angle theta, it's approaching pi, now we're on the negative ray. So we've gone from 0 to pi and we've traced out the 3 leaves. If we continue going, we're just going to trace them out again. And so on as we continue around. Okay, so I'm going to make this available, this applet available, so you can play around with it yourself. There's some fun things you can probably do. Just start changing the r function and see what happens. Change it to a sine 3 theta, and see what happens. Something might surprise you in relation to what happened with the cosine. So yeah, play around with it. And in another short video, I'll show you how to start from scratch and sketch these polar coordinates, these curves in polar coordinates, by converting them to parametric curves. So when we go to sketch these curves by hand, the idea is to try to see visually the relationship between r and theta. How does r change with theta? That typically goes to sketching the graph in the Cartesian coordinate system. And then using that information, try to piece it together to get the polar coordinate sketch. Now the next thing we want to do is we want to bring calculus into the mix. So for example, I pick a point on the curve, I don't know, maybe a point somewhere over here, and I ask the question, what's the tangent line at that point? What's the tangent line? Can we find the equation of the tangent line? So now we're going to start to do calculus on these polar curves.